Okay, so my name is Shreedharan. I've been at StreamSets for about a year. I'm going to quickly talk about one of the customers we have. Unfortunately, I cannot name them, but they are a co-customer between us and the host of this conference, Databricks. And basically, I'm going to talk about their specific use case, how they use various tools in the ecosystem, and actually gain analytic insights about customers who are in retail shopping centers, and use that information to actually improve the way they sell to people, the way they bring products into the store. So quickly, who am I? So I am a software engineer at StreamSets. I've been at StreamSets for just over a year. I work on two of our products, the StreamSets Data Collector and the Dataflow Performance Manager. So these two products are currently available. StreamSets Data Collector is free and open source, Apache licensed. You can grab it on GitHub and play around with it. StreamSets Data Collector is actually a system that is meant for data integration. So, if you compare it, just like, I don't know how many of you were there in Gwen's talk just about 10 minutes ago. She talked about systems that are meant for data integration that can move data from one place to another. And StreamSets Data Collector just does that. In fact, the best part of it is that it can integrate with Spark. It can integrate with Kafka. So you don't actually have to worry about the integration pieces. You can write your own code. You can write your own scripts and modify your data in addition to all of the processing power that StreamSets Data Collector automatically provides built into the code base itself. Now, before StreamSets, I was at Cloudera. I was at Cloudera for just over 4 years. I am the PMC chair for Apache Flume. I worked on Apache Scoop. I'm a committer on Apache Scoop. And I did contribute quite a bit to Spark in my last 1 year at Cloudera. So I actually did much of the yarn integration, the security aspects of the yarn integration, and quite a bit of streaming work before I left. Before that, I was at Yahoo for a couple of years. And I also wrote a book for O'Reilly. It's called Using Flume. So it basically talks about how you'd use Flume, and that's kind of evident from the name, I suppose. Now, what is StreamSets Data Collector? StreamSets Data Collector is actually a graphical UI, but the best part of it is that the graphical UI is just the configuration piece. It's just supposed to make it easy to use. You can actually completely avoid the graphical UI, go JSON, go REST, whatever, right? The graphical UI just makes it easy to use and makes it easy to configure. And it also allows you to process and think about your data pipelines as it would be when it's actually running. So it basically has a bunch of built-in processors. These processors basically modify your data in stream. They don't actually, it's a map operation. So they don't actually spin off a different process or anything. It happens in stream. So again, a reference to the previous talk, Gwen talked about masking your credit cards. Guess what? You can automatically do that with a field masker and just mask the credit card number. Use regexes and use ELs if you have. So all of those things allow you to make it easy to integrate your data streams by changing them within the stream and moving it from one place to another. And it's actually very easy to configure. It's completely in memory. So we never actually spill to disk. So the whole thing's in memory, gives us high throughput. And we actually do micro-batching just like Spark streaming. So this allows us to be in memory and not lose data if there is a failure. It's completely open source. So if you want to actually go and pick it up, see how it's implemented, it's all on GitHub. So, and it's Apache license. So if you want to fork it and write your own connectors and whatnot, go ahead. It's all Apache license. Now, how does an SDC look? An SDC actually has a number of pipelines. Each pipeline basically starts at an origin and ends at one or more destinations. You can always take the data in from the origin and then process it in any way you want, split it out based on some criteria, and write it out to more than one location. And eventually, when you're done with that, you can trigger an event processor to actually go and change stuff in the end. It's called an executor. So one of the most common use cases is Impala. Impala requires you to refresh your metadata once the data is written out. So the Hive query executor can actually talk to the Hive metastore and trigger that refresh for you once the data is written out. So when a file gets closed, Impala requires that that file get added to its own cache, which requires a metadata refresh. That's usually done using the Hive query executor, and it's extremely efficient because it happens immediately after the file is closed. So basically, the idea here is that this is just an example. You can actually integrate with Bigtable, Elasticsearch, Hadoop, Kafka, Databricks, any of these things directly within the stream. All you need is to configure it pretty much using the minimal configuration that's required to actually trigger the job. Right? So if you have Databricks, you have a Databricks account, all you need is the credentials and the job number. And I write to S3 when the objects get closed on S3. I can trigger a job in Databricks to actually use those objects to process the data. We'll talk about that in a bit. Now, in this specific use case, I'm going to talk about how data and sensors can be used to personalize a shopping experience. So this is one of our customers who actually picks up data from hundreds of sensors located across the floor of a retail shopping center. So they have hundreds of shoppers in each center at any given point in time. And there's a lot of data available about these customers who are in the store. One is their location. Where are they? Like, where in the store are they? Second one is, do they have existing user profiles with us? Do we know who they are? And the third one is these user profiles integrated with applications on mobile phones. So these mobile phones actually, most of these retail shopping centers have, if you go to Home Depot or go to Macy's or whatever, you're inside a store, it'll actually tell you, hey, you're inside the store. Do you want to find something in a specific aisle? And it'll show you the aisle number if you search for something. So you can actually go and pick it up. So that kind of information is already available when you have a smartphone and you have the application for that particular retail center available to you. Now, how do you personalize this further? It is possible that you can actually figure out where something is in the store. But is it possible to actually make it even more personal for the user? So you know enough information about the user to actually make it more engaging, better for the user in terms of figuring out what is where and what they would be interested in. Now, in this specific case, the retail shopping center has hundreds of sensors located around the major aisles. So these sensors have a number of connectors. They have Wi-Fi, they have Bluetooth, some of them even have cell phones. So if you have, if you have used AT&T and you don't have cell phone coverage, they have this little thing you can hook up in your house, which will improve the cell phone coverage. Similar things inside shopping centers is pretty common these days because they're so huge. Cell phones don't actually always work. So they have microcells within the shopping center that can improve the cell phone coverage. In addition, that can provide usable insights into the data of the users. Now, what do these sensors collect data? What data do these collect, and how do they collect it? So one of the most common use cases, I won't talk about all of them, one of the most common use cases is to do a partial Wi-Fi handshake. So the Wi-Fi handshake doesn't actually log you into the Wi-Fi of the retail shopping center. Instead, it gets a unique ID for your mobile phone into the system of the shopping center. Now, using this and multiple sensors located around the shopping center, we are able to track an approximate location of the user. So now, if a shopper is in the store and they're in a specific location, you think about it like GPS. Based on multiple sensors, based on the distance, you can sort of figure out where you are. Now, it's only approximate. You can't figure out exactly where you are. But using an approximate location and how you move, foot traffic patterns can be figured. So now foot traffic pattern is calculated simply using this information. Now, this also means that a unique user's location and which stores they spend time in, which aisles they spend time in, can be gathered using this information. Now, if you have an app, that integrates even further with this, because now you know that this user is spending time in approximately these areas, and the app actually collects even more information about, hey, did you search for going from location A to location B? Did you go from cosmetics to whatever, home goods? So this information is available through the app if you actually search for directions, if you are actually looking for a specific aisle. So now these things can actually be used to send specific information, specific promotion, specific updates directly through the app to the user. Now, if the app has a registration, it's possible that there's SMS sign-in, there's email sign-in. That's additional information which can be used to actually send more personalized information to individual users. The problem with all these sensors, though, is that they are really stuck to protocols which are not always used by everyone. Like, these sensors don't have a JVM running on it. They don't speak Kafka protocol. You can't really have a Kafka client sitting on these tiny little sensors. They almost always have protocols which are a little obscure, which you don't usually have clients in your application for. You don't actually want to maintain these clients either. In fact, I don't even know the full forms of a couple of these. Like, my colleagues wrote these connectors. I don't even know the full forms of many of these. But the common ones are CoAP, HTTP, TCP, UDP, WebSockets, MQTT, OPC UA. I don't even know what the last one is, but these are protocols which are pretty common among connectors, it seems, among sensors, it seems. Now, the problem with all these things is that you can arbitrarily increase the number of sensors and increase the amount of data you collect, but how do you scale? How do you increase the ability to actually process the incoming data? So you can add more nodes and process it as and when you receive more data. So streamsets actually is the use case here. They actually use streamsets to connect to these sensors directly. We collect they run the streamsets data collector, collect the data, and process it as it comes in. Now, they use multiple different protocols here because they have different kinds of sensors. They speak different protocols. But we support these origins, which they directly send data to. And as they need more processing power, they simply add more streamsets data collectors. They just add more data collectors. And initially, they were on-prem. Then they moved to the cloud. They just added more data collectors there and configured their system to actually just send the data to these data collectors. So as and when they required more processing, they could just scale up and scale out, depending on if they were running on-prem or in the cloud. In the cloud, they could just do a bunch of containers, which they could just scale out. Like I said, most of what we do is in memory. So they didn't actually lose any data when their containers went down, when they scaled down because, hey, it's nighttime. There are no shoppers actually shopping in the center. So depending on whether you're on-prem, whether you're on the cloud, SDC made it really easy for them to actually scale out and scale up because we could actually directly connect to these sensors. The other important thing was data formats. We support a bunch of data formats. This helped them actually integrate directly into the SDC by saying, hey, my incoming data is actually JSON. It's Avro. And they didn't have to worry about writing a parser and getting the data into a format that they could process. Instead, we will actually transparently convert this into JSON, into an SDC record from JSON, Avro, or whatever. And SDC records, depending on your data type, incoming data can be like lists or maps or whatever. And these SDC records can actually directly be processed using a bunch of connectors and processors we provide, including Spark. The best part about having an SDC record is the concept of an intermediate data type. The idea is that the middle, whatever you have, is an intermediate data type which SDC understands. Now, if your destination is S3 or HDFS or two different destinations, and they require different data formats, sure, just you have a drop-down. You select, oh, that one is JSON because I have some Python application reading it. And the other one is simply going to be Avro because it's HDFS, and I'm going to trigger an Avro to Parquet job later when this file is closed so that it can be picked up by Impala. So things like that can be done directly within the SDC without actually having to hand code jobs, hand code these conversions. That's what the use case really here was. The customer did not really know who their customer would be. So they needed to figure out a way to actually make it easy to not have to hand code all of this. That's where SDC provided value, and that's where they integrated with SDC by reading their arbitrary protocol into SDC and then writing it out. To process the data, they actually had in-stream processing to just have processors which modified the data, which are simple map operations. So the map operations would just read the data out and just convert them as is. So most of them would be a record-by-record change, usually a field masker or a field, changing the timestamp data type, right? Like from changing it from long to a string, which is human readable, things like that. So these were just map operations. Now, scripting processors are where you can actually write your own scripts, where JavaScript or Python or Groovy or whatever, and change the data in batches. So you have a whole batch of records. You can drop arbitrary records which don't match your use case, or you can actually increase the number of records. It doesn't matter. So these are really code, custom code, which you can just embed into a text box, and then we actually evaluate it directly. The most interesting one, which I think was added recently, is the Spark Evaluator. Spark Evaluators allow you to specify a Spark job. So you write Spark applications in any JVM language. For now, we don't actually support Python, so you can write Java or Scala and embed the jar into the configuration. Once you embed the jar, we'll actually run the Spark application for every batch of records. It's roughly equivalent to for each dstream if you use Spark streaming. So for every RDD, every microbatch, we generate an RDD of records. That records, you can actually change it in any way you want. And then eventually, you don't have to worry about whether your destination accepts Avro, because again, you can just write it out as Avro, and it's directly supported. The best part about this is you can actually isolate your Spark application from completely figuring out where the data comes in from and where it's going. All you have to worry about is your app. The origin and destination, you can leave it to SDC to actually figure out how to use it. That's exactly what the customer did here. They actually used SDC to do their Spark modifications, and they didn't actually worry about what the destinations were because they were actually using multiple destinations. They didn't want to embed that into their Spark code because they actually had on-prem, hybrid. They even had 2 different clouds. So they didn't want to say, hey, I want to write to S3 and then have the S3 code written out in their Spark application and have different application to talk about Google. So all of that stuff can be completely separated out, and SDC will take care of it for you. In cluster mode pipelines, you actually see all of the data coming in per microbatch from Kafka. So it's exactly like how you use the direct stream in Spark streaming. You would actually read the data directly as a microbatch, and each batch represents exactly one partition in a Kafka topic. So that way, you can actually ensure that you would read all of your data in parallel. So if you want to scale out, just increase the number of partitions in Kafka, and you automatically scale out. This is sort of how the Spark Evaluator works. You can actually have multiple SDC stages on both sides. So you can have your masking and renaming and whatever before the Spark application, process it, and then ignore records which are not required on the other side. And if certain records cannot be processed, they're dropped into an error stream, which gets written out to an error sink, which can be S3, which can be HDFS or anything like that. So that way, you avoid having to deal with, hey, what happened if I couldn't process it, right? You just drop it out into an error stream. That's it. And it gets pushed out into whatever the error sink is. You can use MLlib. You can use machine learning, any of these things within the evaluator to actually improve your analytic use case. In this case, they were not actually using MLlib. These were mostly simple map operations and figuring out how their data looks like and what kind of processing they need to do eventually. Now, the transformer, which is the piece which you would write, which actually returns both the errors and the processed records. Now, the processed records are then written out to the next whatever system is processing it. So it goes out into Cloudera, into MapR, whatever. The Spark Evaluator today supports Cloudera and MapR versions of Spark. So you can run it on a CDH or a MapR cluster. So in this specific use case, the Spark Evaluator was used for a couple of things. One was to figure out if a specific transaction was actually fraudulent, if the customer was actually present in the location where it was claimed to have happened. So things like that, anomaly detection, sentiment analysis, NLP can be done in real time as the event stream is collected from these sensors. The use case in this specific case was to actually do real-time feedback, which is promotions and fraud detection based on whether the user actually was present in those locations. Today, SDC on Spark actually supports only one origin, Kafka, but in MapR, it's MapR streams, so it supports that. But destinations, is pretty much everything that SDC supports. So HDFS, HBase, Kudu, S3, any of these things. This is just a short list here, but the number of destinations is actually incredibly huge. I can give you an example. If you build just SDC and build it with all of the libraries and all of the connectors, I think the total size goes up to over 2.5 gigs. So that's just the jars that it downloads. So because of that, you can actually think about the connector framework we have in there, which actually is bundled with SDC itself. And there's a pretty good ecosystem of third-party maintained connectors, which we don't actually have in our code base, but somebody else is maintaining it. Now, the Spark executor is the more important piece, which the users were actually using here. So the Spark executor is basically this. You have data coming in, and data is written out. That arrow can have multiple processes in between, but let's ignore that. And for now, the data just gets written out to, say, Hadoop. And at the end of that, you have the file being closed. An event is triggered, which can actually run a job on Spark. Now, in case of Yarn, in case of CDH or MapR, that would be a MapR or CDH Spark job. Now, the more important one we're going to talk about here is the Databricks integration. So what we essentially do is we can trigger a job on Databricks where you have already configured the job and you give us a job ID. We can trigger that automatically for you. So that event can get triggered by your file on S3 getting closed, or your file even in HDFS getting closed. But I don't really know why you would use HDFS with Databricks, but if you want to use that, sure. Today, we have Yarn and Databricks Cloud support. So now, at the end of your write to S3, an event is triggered saying, hey, this is my file which just got closed. This is the name of the file. And it's passed to your application. And your application can actually use that information to trigger a job which would process the data in the file. In the Databricks Cloud, you can actually do a jar or a notebook job. And in most cases, what you've seen is people tend to use notebook jobs because they're easier to edit, they're easier to use, and that actually allows for more experimentation. So we actually can pass parameters to both jar and notebook jobs. And these notebook jobs actually have Databricks dbutils.widgets, which can allow you to pass parameters via the REST API, which is what we use. So now, in this specific use case, the S3 file is closed. And the S3 file actually contains a lot of information about the user patterns and all those things, which gets written out. Now, once a file gets written out, we pass the object name in as a parameter to a notebook job. This job actually reads the data directly from S3 and processes it. So we never actually pass the data out to the Databricks job. Instead, Databricks directly reads it from S3. And you can pass additional parameters, and the parameters are completely configurable. But in this specific case, it's basically the file path. And now the notebook integration is used for really easy experimentation. It's trial and error, improving the current job without actually rewriting and recompiling, re-uploading, re-triggering the whole thing. Now, you could actually even change the job between file closes, and we wouldn't actually have a problem because we basically just use the job ID. Now, this is basically used for what are really batch jobs, model creation, figuring out classification algorithms and such, which are just batch jobs, and they don't really need to happen in real time. They don't actually create real differences as the job is running. So conclusion is that Spark is excellent for in-stream and end-of-batch processing. SDC makes it easy to do so. So in this specific case, they actually used SDC plus Databricks Cloud to make batch processing a really easy by just using the notebooks and just updating their job without actually having to reconfigure and retrigger any of the stuff. Now, notebook integration is something that many customers have actually tried out and have increasingly started using. But just FYI, you should probably use jars for production jobs and not keep notebooks around for production. That's pretty much what I have. Do you have any questions? I know this is the last talk of the conference, so half of the attention is pretty much at the door. So if you have any questions, you can ask me now. I have to go a little fast. I had to go a little fast because I'm doing a talk in about 20 minutes in a place which is 20-minute walk from here. So, so if you have any questions. OK, great. Thank you very much.
Thank you very much.
If you have any questions, I'm going to be at General Assembly in 20 minutes.